Guys, in the previous video I made, I went over the 7489, which is 64-bit or 8 bytes of RAM, and it's a 16-pin chip, and it has 4 address pins, 4 data input pins, and 4 data output pins, and 1 memory enable pin, and 1 write enable pin. And in this video we're going to go over what all of these pins do and how to use this chip on a breadboard. So this chip is a little bit more complicated to use than most RAM chips. It's not really that complicated, but basically you start out, you want to hook up your ground to pin 8 and your power to VCC pin 16. And then you have these 4 address pins, and the address is basically just a memory location. So you have 4 address pins, and each of them denotes 2 to the power of whatever. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. And I'm pretty sure these are multiplexed. So the way that you can think of it is, basically if you enable this address, you're at 2 to the power address 2 to the power of 0, which is address 1. This one would be 2, this one would be 4, and this one would be 8. Now, hypothetically, let's just say you turn on A3 and A1. The address you would be at in decimal would be 10. And if you wanted to be at the final address, which is address 15, you would have to bring all of these pins high. So its address is 0 through 15, so it's got 16 addresses, and each of them holds 4 bits of data. Now, something that's a little annoying about this chip is its outputs are inverted. So it has a little bar over its outputs. So the way that we're going to fix that is using a hex inverter, the 7404. Now we're going to use this chip for 2 reasons. The first reason is the outputs of this chip are not able to for the 7489, they're not capable of syncing enough current to the outputs to power on the LEDs. So this chip acts as kind of a small amplifier and also as obviously an inverter, so that we get the correct output based on our input. So back to the data sheets, we'll put them side by side. So this one is a hex inverter. So it has 6 A's, and those are the inputs, and then it has 6 Y pins, which are the outputs. And I don't think I need to say this, but if you put a 0 on an A, you get a 1 on the Y. You put a 1 on the A, you get a 0 on the Y. So it has 6 of those built into it, and obviously power and ground. So I have the previous chip wired up already. So let's go through all of the wiring again. So pin 16 is to positive, pin 8 is to ground, pin 1 is A0, and that is connected over here. And then the other 3 address pins over here, I have them all connected to ground currently. I also have all of these data pins, D1, D2, D3, and D4. These orange wires, they're all hooked up to ground. The memory enable, we want to bring that low to be able to enable the chip. If you bring it high, you'll disable the chip, you won't be able to read or write from it. That's for if you have multiple of these chips connected and you want to do memory banking. We'll get into that maybe into another video. But the other pin that you have is the write enable, which also is active low, so I have it high, and if we ever want to write data to a memory address, we'll bring it low. So I'm going to go ahead and hook up the outputs of the chip to the 7404 hex inverter. So I'm going to pop it into the breadboard like that and grab a few wires. So we need to hook this chip up to power and ground. So I'm going to do that right now. Power, and let's also hook up ground. Next, what I want to do is take all of the outputs of this chip, the 7489, and hook them up as inputs to the 7404. The reason I want to do that is, let's say the output is inverted. If we put it through another inverter, the output of that inverter will be the inverted output, so it'll be the non-inverted output. And you'll see that after I'm done. So I'm just going to take all of these output pins. So we've got Q1 and Q2, Q3, and Q4. So I'm just going to get all of those. So let's get in here. So I'm going to get this Q1 and also Q2, Q3, and last but not least, I'm going to get Q4. Okay, great. So next I'm going to hook them up to these LEDs. So Q1, which is right here, will go to this LED. And then this one right here. This one here. And this output to right here. Perfect. So now that everything is hooked up, we could do a couple of tests. So right now we're in address 0. I'm going to go to address 1. And there's some garbage written in there. So all of my data pins are hooked up to 0. So I'm going to write that in. And oops, that's not the right enable pin. Here. So I'm going to put the right enable pin low. And you see, I cleared that address. So what I'm going to do is I'm going to put a little pattern. So I'm going to put 1 0 1 0 into this address 1. Okay, so I'm going to bring the right enable low. And there we go. You could also hook this up to a push button and hook these up to dip switches as I did in my other video, but for the sake of this I think it's easier to see it like this. So 1 0 1 0 and address 1. So now if we go back to address 0, our 0 will be in there. Let's go to address 2. Address 2 also has some garbage in there. Oops, lost the pin. Ah, come here, wire. Let's put this wire to high. Come on. That's frustrating. Just want it to go high. There you go. So I'm just going to write a 2 into memory address 2, because why not? I'm going to bring this right enable low, and we've got a 2 in address 2. Now let's go into address 3. So I bring the first 2 pins like this, and that one also has garbage in it, and then we can write in a, I don't know, a 6. Why not? So let's put a 6 into address 3. There we go. Now you might be like, who cares? Well, we could access all of these addresses again. So we could go back to address 2 and our 2 will still be in there, as you can see. And then we could go to address 1 and that little pattern 1 0 1 0 will be in there as well, as you can see. And obviously back to address 0, our 0 will be in there. So I'm gonna grab a pen real quick and show you guys a little bit more clearly what's going on here, because you might be like, how are you accessing 16 addresses with only 4 pins? Well, this is how. So these addresses are all in binary. So let's say you have A0, A1, A2, and A3. What these are basically is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. And it might help to write it like this. 2 to the 3. So let's just say do 1, 1, 1, 1 on all 4 address pins. What you will get is 2 to the 3, which is 8, plus 2 to the 2, which is 4, plus 2 to the 1, which is 2, plus 2 to the 0, which is 1. And that's equal to 15. Now, if you set these all to 0, obviously what you're going to get is 0. So we have addresses 0 through 15. 0 counting as an address, so it's inclusive. So we have 15 memory locations, and each of them can hold 4 bits. And this is a 4-bit number as well. So we have a 4-bit address bus and a 4-bit data bus. So you could see that that's why we have 4 wires for each. And just for the kicks, let's look back at the address 1, look back at address 2, and then let's look at address 3 again. So yeah, all of that data that we put in there is there. So yeah, I'm hoping that this made it extremely clear how to use the 7489, what its uses are. One other thing you can do with these 7489s is put 2 of them together to get an 8-bit data bus. A lot of people do that. But what I prefer to do is to use a bigger RAM chip, such as, you know, an HM6264. This one has an 8-bit data bus, and I think it has 15 address lines or 14 address lines. So this could store a lot more data. But the difference is the outputs and inputs are the same. So all of the input and output pins are the same when you switch between input and output mode. This one has separate data inputs and data outputs, which is kind of an older way of doing it. As you can see, it's from 1972. So yeah, that's pretty much it, guys. Thank you for watching, and I'll see you guys next time.